This chapter is all about the E's and the LNs, right? It's called the transcendental functions. It's just a fancy name. Just talk about the natural log with the LN and the E's, and we'll do different bases later on. But this chapter, we're also going to combine derivatives and integrals all in the same chapter there. So I think each section by itself is actually pretty darn simple. We're just going to learn a property, practice it, learn another property, practice it, and then we'll merge them all together. We'll have a study guide for you, kind of working with all that stuff there. Before we start the calculus part, we need to review just your pre-cal properties. So I would just pause it for a second, get those pre-cal properties down. These are your 3 log laws that work in both directions, like how to condense it and how to break that stuff up there, how to expand it out. So we use those quite a bit. These work for any base. I just wrote them down again over here with your natural log, with your ln. So if you have the ln of a times b, you're allowed to break it up, make it the ln of a plus the ln of b. So we'll do that a lot when we do our derivatives. If we're solving equations, a lot of times we want to condense and put them back together right there. And we're allowed to pull the exponent down in front, break the stuff up with the addition, subtraction stuff there. So make sure you know your 3 log laws. Also, what we use quite a bit is the main definition of the log, where if you have log base b of a equals c, you can rewrite that as b to the c equals a. So we need that when we solve equations with these things. So make sure you know, if you know pretty much your 3 log laws and your main definition of your log, you should pretty much be able to solve all of those pre-cal solving type of problems right there. So we'll give you a little bit of practice that in the homework, and then we'll just give you a bunch of derivatives right there. Also, what we should be able to know without the calculator is what the basic graph of that log graph looks like. And also without the calculator, that the ln of 1 is equal to 0 and the ln of e is equal to 1, all right? So we'll just keep seeing those a bunch once we start doing integrals with this stuff there. So we want to make sure we always kind of know those, and we got to expect to know those without the calculator on the actual AP test on the non-calculator portion there. So make sure you get your log properties down, and we'll practice those and we'll use those as we're doing our derivatives. And then the derivative part. So now we're just focusing on how to do a derivative of a natural log. That's all this section is. It's a really, really easy property. So if you have the ln of something, when you take its derivative, what you do is you go 1 over that something times it by the derivative of that something. That's your property. We're just going to practice that, and then we'll combine it with some stuff that you already remember from the chapter 2 days, all right? So if you have y equals the ln of x, so what you're going to do, you're just going to go 1 over x, and then you're going to times it by the derivative of x, which is just 1, and then you're done. If you have a number in front, that number could just, so if I have 3 ln of x, when you do the derivative of the ln part, that's going to be 1 over x times the derivative of x, which is 1, but then you're timesing it by 3. So if you have like 5 ln of x, it's just going to be 5 over x. So the derivative ln of x is just 1 over x. If you have something other than an x, right, just follow this property right here, okay? So if you have the ln of a sweatshirt, you're just going to go 1 over that sweatshirt, just drop that down to the bottom and rewrite it. And then on the top, you times it by the derivative of that sweatshirt. So the derivative of the x squared minus 2 is just going to be a 2x, and then you're done. So that's really the only new thing in this section. And then we'll give you a few harder looking problems, and we'll make sure we do the pre-cal properties first to make it easier on ourselves there. And then we'll just practice those derivatives right there. The next example is what you're going to hear me start to say is what we did in the derivative chapter when we first learned derivatives. I would say, what is that? Is that a power? Is that a product? Is that a quotient? Is that a trig function? So then that would determine whether we start with the product rule or the power rule or the quotient rule or a trig problem right there. So it's the same thing here, but now we have an added thing as we could say it's a logarithm. So if I say, what is this? This is a log derivative because you have the log of something. So who cares what that is? That's just like your hooded sweatshirt right there, right? If you have the log of something, you just ignore that. So you just follow this property. That's all that's going on right there. So if I have the log of something, I'm going to go 1 over that thing, just drop it to the bottom. And on the top, you're going to times it by the derivative of that thing. And then we got to know that the derivative of sine is going to be cosine. So, I mean, that's a pretty solid answer right there. Just a simple fraction with sines and cosines. If you want to make that the cotangent of x, you can. When you do some of these problems in the homework, a lot of times they might put absolute value bars instead of the parentheses. I want you to just ignore the absolute value bars, just treat them like the parentheses, and then just do the answer like normal, okay? We will fine tune why they're doing that when we learn the integrals there, but we're gonna assume everything we're doing is in our domain anyways there. So don't even worry about the absolute value bars, just treat them like parentheses and then just take your derivative there. All right, so when I look at this next example, if I say, what is this? Is that a power, a product, a quotient, a trig problem, or a log? This is a product because you have something with a variable, all right? So that's different than if you have a constant, but if you have something with a variable and you're multiplying those two things together, this is a product. And so if you recognize that that's two things being multiplied together, that means I got to do a product rule. So if same things, if I gave you x over the ln of x, that would be a quotient. Do your quotient rule on that problem right there. And then the only difference is when you do the derivative of the ln, you're going to use this new property right here. Okay, so it really gives us a chance to shore up any sort of derivative stuff and just stay sharp with our derivative skills in this section, in this chapter there. So if I do my product, I'm going to go first function, just write it down. We'll times it by the derivative of the second. So here's our new property. If you have the ln of x, that's what we just did up here. The derivative of ln of x is just 1 over x. And then we're going to go plus the second function. And then we're going to times it by the derivative of the first, but the derivative of x is just 1, so I'm not going to write anything there. And then I'm realizing that these x's will just cancel out. And then we get 1 plus ln of x as our derivative. And then remember, everything you know about derivative is still true. That's still going to be the slope of the curve, the slope of the tangent line. So if I give you a problem, say find the slope of the curve, you plug that in right there. Plug in your x right there. If you find the equation of the tangent line, you take your derivative, plug in the point to get your slope, and then you can do your point slope form, get the equation of your tangent line. All right, now these next two examples, what I want to stress, there are long ways to work out these two problems. Typically, the people who choose the long way to work out those problems are the ones who screw that up on a testing situation. Use your pre-calc properties first, okay? If you have the log of a product, the log of a quotient, what I want you to do is use these couple of pre-calc properties first. If you do this, right, if you go 1 over that stuff times it by the derivative of stuff, you're going to go 1 over a fraction. So that fraction is going to be on the bottom. And then when you do the derivative of that on the top, you're going to have a quotient rule on the top. You should not find yourself doing that, okay? Right here, look how bad this would be. You would go 1 over that giant square root on the bottom. And then if you went straight to the derivative, if you went straight to this on these problems, how bad that would be. You would go 1 over that radical, and then you do the derivative down on the top. So you would have to raise that to the 1/2. You would multiply by the power, leave the inside alone, decrease the power by 1. So you would have 1/2 times that stuff to the negative 1/2. Then you would need to times by the derivative of the inside. Then you need to do that quotient rule. So you got a power rule and a quotient rule all over that square root. The simplifying on those things is just ridiculous. These problems should be easy. If they're not easy, you're probably making it way too complicated on yourself there, okay? So that's why I stress, if you have, I'm not saying that you won't ever use a product rule or a quotient rule. We just use a product rule on this problem because it was a product right at the very beginning. I would use a quotient rule on this problem because it's a quotient at the very beginning. But whenever you have the log of a product or the log of a quotient, break that stuff up. Break it up first before you do the derivative. And then after we do the derivative, we'll get our one single fraction like we always do. So it helps out on the max and min problems. But break stuff up before you take a derivative, and then we'll put it back together after we take the derivative. So that's why I want to stress, just please use your pre-calc properties first. I can't stress that enough. So watch how easy this is going to be. So I'm going to rewrite this as the ln of 2x plus, I'm sorry, minus, that's a quotient right there. So we're going to go minus the ln of x plus 3. All right, now I can technically break this one up further, but once you get simple things in there without the fractions involved or the square roots and stuff involved, that's going to be really nice for us to work with, okay? So now I use my pre-calc properties first. Now I can just take the derivative of each piece. So if I have the ln of 2x, I'm going to go, when I do the derivative, I'm going to go 1 over that 2x, and I'm going to times it by the derivative of that 2x, which is just 2. And then I do the derivative of this. So I'm going to go 1 over that x plus 3 times it by the derivative of the x plus 3, which is just 1. And then right here, it simplifies to this. And then so after we take the derivative, remember, ever since we started the product and quotient rule, we said we should be able to get one single fraction. If you have fractions broken up for your derivative, you want to get one single fraction, because that's what we did coming from a couple chapters ago when we did all those max and min problems right there. So after you do the derivative, break it up so it makes your calculus part really easy. You got your calculus points there, you got your derivative accurate, and now we want to just get our common denominator one single fraction. So I'm going to use the x plus 3 as my common denominator, which means you're squeezing an x plus 3 on the top and the bottom here, and you're squeezing in an x on the top and the bottom here. And then so those x's will cancel out. And then we got this for our final derivative. It's always going to be easier for us if we use those pre-calc properties first. So just practice that. We're going to be good. So let's just do a harder example. We pretty much got all of our examples here for you, but let's just do a harder example so we're prepared for stuff like that. What I'm going to realize that this whole thing is raised to the 1/2. So if I use that third pre-calc law, if I have something raised to a power, I'm allowed to drop that down in front. So I'm going to do that. I'm going to drop that down in front. So I'm rewriting this as 1/2 times the ln of that fraction. And then if you have the ln of a product or the ln of a quotient, use your pre-calc properties first before you go straight. Don't go straight to that. Use your pre-calc properties, break this stuff up first. So I'm still rewriting the original function. So the 1/2 is just out there, okay? And then we're gonna have the ln of the top piece minus the ln of the bottom piece. So I use my pre-calc properties first, broke that stuff up. I can also take this too and drop that down in front, but once I have the ln of x squared, I can do the derivative of that just as easy as I did this example up here. So typically once I make those simpler for myself like that, I usually just jump straight to the derivative. But if you want to make that 2 ln of x and then to do the derivative of that you're certainly welcome to do that there. So now once we take this derivative, so this constant I'm just going to carry down in front. I'm going to do the derivative of each piece separately there. So I'm going to go 1 over that stuff, times it by the derivative of that x squared, which is a 2x. And then ln of x squared plus 6, we're going to go 1 over the x squared plus 6, times it by the derivative of x squared plus 6, which is going to be a 2x. I'm going to simplify this. I realize that these x's can cancel out. So I can cancel out one of those. So this is really just 2 over x. And then remember, if you have the fractions broken up, you want to go ahead and get yourself a common denominator and get yourself one single fraction here. So I'm going to use x squared plus 6 as my common denominator, which means I need a 2 and an x squared plus 6 right here. I'm going to put an x on the top and the bottom here. So if I times that by an x, that's going to make this a 2x squared. This 1/2 is still there, so I need to just remember that. And then we're just going to distribute and combine like terms. I'm going to use a different color here. So this numerator, all right, so these 2x squares will cancel each other out. And then I have a 12 on the top, and I'm going to do it divided by 2. So half of 12, that's going to give me a 6. And there's my final answer for that derivative right there. All right, one final example is just to review the implicit differentiation when you don't start off the problem with y equals something. So one final problem, that's it. A few more minutes of paying attention. If you don't have y equals, remember this is your implicit differentiation where you just take the derivative of everything as is, and if you take the derivative of y's in it, tag on the y prime. You rarely ever want to like try to solve this thing for y, even if you can. That's going to involve, you know, the e's, which we don't quite know yet. So involve inverse functions later on, which we don't quite know yet. So just, it's always going to be quicker for you just do the implicit differentiation. So if I don't have y equals, let's just take the derivative of everything as is. All right, so if I have the ln of a product, so what I'm going to do is I'm going to use my pre-calc properties first. So I have the ln of a product. I'm going to rewrite it like this: ln of x plus the ln of y. So I just rewrote that original function, and now I'm going to take the derivative of each piece separately. So the derivative of ln of x is just 1 over x, right? If I do the derivative of ln of y, you're going to get 1 over y. But once you get your 1 over y, since you took the derivative of y's in it, you got to tag on the y prime. And the derivative of 5x is just going to be 5. The derivative of 30 is going to be 0. And all we're going to do is solve this equation for the y prime, and then we are done. So I'm going to move the 5 over. I'm going to move the 1 over x over, just, you know, subtract those over to the other side. And I'm just going to multiply both sides by the y. And then we're good right there for our first derivative right there. Thank you.